Hello everyone, we have reached chapter 8. In chapter 8, this is the beginning of our work in inferential statistics. So the first 7 chapters we talked about some descriptive statistics, and then we went through about 3 or 4 chapters talking about probabilities. We talked about sampling distributions, and we also talked about the central limit theorem. Now, beginning in chapter 8 and going forward, we're looking at chapters 8, 9, 10, 11, and 12. Chapter 13 for us, the chi-square procedure is going to be optional, so we're going to omit that section, or in that chapter rather. So from here on, we're going to cover chapters 8, 9, 10, 11, 12. And of course, beyond this, we will look at chapters 14 and 16. Okay, so this is the beginning of our inferential statistics work. Remember, in this portion of statistics, here's where we actually like to now generalize to the population. That is, to the parameters of the population from the sample statistics, the known quantities of the sample. So things get pretty interesting from this point onward. In chapter 8, we're going to look at confidence intervals, and we're doing it more specifically for one population mean. That's mu, right? The population mean. There are 4 sections in chapter 8, and in this video we're going to take a look at section 8.1, estimating a population mean. And of course, we're going to go through all 4 sections in chapter 8. Okay, so that's what we're going to do. Now, I have actually written down some of these definitions and terminologies that we're going to be talking about. I have written these so you don't have to watch me write these as I go. It just makes the video a bit longer. So I'm hoping to cut down on the amount of time each video is, the length of time for each video. Anyhow, so here we go through this. Now, before we actually talk about confidence intervals, let's talk about point estimate. Remember, what we're doing in chapter 8 and beyond, chapter 9 and so on, we would like to be able to estimate the parameter or parameters. These are the unknown of the population. Okay. Now, there are a couple of ways we can do this in chapter 8. One is to use a point estimate. And I have written down the definition of what a point estimate is. So a point estimate is going to be a single value. This would be like a point on the number line of known statistic that is used to estimate the unknown parameter of a population. Now remember, statistics are known quantities from the sample, right? And parameters are the unknown of the population. So that would be a point estimate, the value that we use from the sample to estimate the population parameter. The statistic itself is called an estimator. Okay, so that's what the estimator is called. It is called, that's what the statistic itself is called. It's called an estimator. We underline that. So we use those terms interchangeably, statistics and estimators. Now, there are 2 types of estimators, by the way, in our work. We have what we call unbiased, and we have biased estimators. Now, biased doesn't sound good. Unbiased estimators are the ones that we actually like, and that's the one that we would like to use. So what is an unbiased estimator? If the average or the center of the sampling distribution of a statistic, which is our estimator, turns out to be the same as the parameter that the statistic is trying to estimate, then they call that estimator an unbiased estimator. That's what that is, unbiased estimator. So remember, the center of the sampling distribution, the probability distribution of the statistic, will be the same as the parameter that we want to estimate. So let's take a look at an example here. So for my parameter, since we are in chapter 8, I have selected mu of x. That is the mean of random variable x. Now, just to point something out, by the way, in your book, the author does not use a subscript of x. He just uses mu, and then he assumes that's for random variable x. I like to actually carry the subscript on mu because, as you will see, we have two different random variables. So that way I can distinguish between the two random variables. So mu of x would be the population mean or average of random variable x. And the point estimate, the estimator that we're going to use to estimate it, is x bar, its counterpart in the sample. So the sample mean of random variable x, which is x bar, is going to be the point estimate of that. And it's really that simple. So if you want to estimate the population mean, you use the sample mean. That's what this says. Now, the sampling distribution of x bar, remember we talked about the central limit theorem in that was the last section of chapter 7, I believe. CLT, central limit theorem. And if you recall, central limit theorem told us that regardless of the population that you sample from, the sampling distribution of the sample means, which is the mean of the means, is going to be approximately normal, or normal, depending on whether you sample from a normal population or any population, with mean, which is the same as the mean of the random variable x, and its deviation was sigma over root n. And we looked at that in chapter 7. So now we know that mu of x bar would equal to mu of x. That is because of central limit theorem. That's this part that I have highlighted. Now, remember also, please keep in mind that the mean mu of x is going to be unknown throughout our work. And that's what we're doing this whole work, because we want to estimate it. Now, because the mean, and this is what this unbiased estimator was telling us, if the center of the sampling distribution of the statistic, so here x bar, this is our statistic. Okay, that's our statistic. And the center of its sampling distribution, that's right in here, that center is indeed the parameter we want to estimate. Now, we want to estimate mu, right? This is what we would want to estimate. So, in other words, that makes x bar an unbiased estimator of mu of x. And again, that's a good thing we would like to have. Now, the other kind of estimation, by the way, is going to be interval estimate. So what is an interval estimate? These interval estimates, by the way, we know them, we call them, everybody calls them confidence intervals. Okay, so what is a confidence interval? A confidence interval is a range of scores, a range of values, which would be in the form of an interval, based on the point estimate. Okay, and this interval is where we believe the parameter is located in. So that's what a confidence interval is called. Now, for every confidence interval, well, that was interval estimate, I'm sorry. Now, what is a confidence interval? A confidence interval is going to be the certainty level that's expressed as a percentage associated with a confidence interval. Okay, let me see. That's actually confidence interval. Oh, let me correct this one. We're talking about not an interval, because I already talked about interval estimates. Let's talk about confidence level here. Let me correct that. We're talking actually about a confidence level. Okay, that's what we're doing. A confidence level. So what is a confidence level now? A confidence level is going to be the certainty level. There you go. Now it reads well. The certainty level, and usually this confidence level is going to be a percentage. Okay, that we associate with every confidence interval. Okay, and this confidence level tells us how confident, how certain we are, how sure we are that the proposed interval actually might contain the parameter that we're trying to estimate. Okay, so that's what the confidence level is. Now, the typical confidence levels, to give you an idea, let me write these. The typical confidence levels are 90%, 95%, and 99%. So you can kind of see that the higher the confidence, the better we feel about our estimates. Okay. Now, we'll see later on that the higher the confidence is going to come with a cost for us. The cost would be the sample size, the higher sample size. So, now here's an example that's actually in your book. Okay, and once we see this, we'll actually go to StatCrunch and we'll take a look at this ourselves in a different form. Now, in this exercise or example, what the author has done is he has built 20 confidence intervals for the average price of all new mobile homes. And these are each based on a fixed sample of size 36 mobile homes. So he wants to make sure that he satisfies central limit theorem. Remember, sample size must be at least 30 if we don't assume normality of the population. So 20 confidence intervals, and how he's done it is he's used a formula. But don't worry about the formula yet. It's just he has actually constructed, and there you go. Now, these confidence intervals are based on a confidence limit of, I know it kind of sounds odd, 95.44%. Why 95.44? Why not 95? Well, 95.44 is exactly 2 standard deviations above, 2 deviations below the mean. So that's what he had in mind, the author, when he did this. He wanted to take a look at an interval based on 2 deviations above or below. Later on, we actually choose our own confidence levels based on the numbers that I just mentioned earlier, 90, 95, 99. So, now for this exercise, he so happens to know that the average selling price of a new mobile home is $65,000. These numbers are in thousands of dollars. And there's you go. There is mu. Now, remember, seldom we know this, but somehow he knows that information. So wherever his source might be. So this is true mean, which oftentimes would be unknown for us. But for now, let's say we know that it is 65. So look at this confidence interval he established. Well, first, he took a sample of size 36 new mobile homes. So let's say he went to Chula Vista, being our locale. He went to Chula Vista and sampled 36 new mobile homes. The average price of those 36 mobile homes was $65.45. Okay, and then he did it from a second location, another sample of size 36 mobile homes. And note, by the way, each of these samples have different average. You see that? That's why X bar itself is a random variable. See how it varies? And it's random because if he goes to, let's say, the 21st location to choose a sample of size 36 mobile homes, he's not going to know ahead of time anyway what that average is going to be. So all of these means are different, and every one of these is an estimate, a point estimate, a single number guess at mu. So 65.45, pretty close. 64.21, not bad. Not bad. This one is off a little. It's below 64. So I'm thinking anything between 64 to 66, he's doing a good job. This one close, 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 and so on and so forth. Okay. Now, over here in this column, he has constructed these confidence intervals. So look at this confidence interval. He's 95.44% sure that the true mean is somewhere between $63,000 and $67,850. That's my first confidence interval here. Okay. Now, to the right of that, it says, is mu in that confidence interval? The question mark. Is mu in there? Remember, mu is 65,000. Well, mu is somewhere in here. Sure. Yes. Look at his second confidence interval. Is the mean $65,000 in there? Sure. Yes. Next one. Yes. 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 So most of these have the true mean captured inside of it. Look at this one, for example. This one predicts the average cost of a new mobile home ranges somewhere between $61,450 to $66,250. And the true mean is $65,000, right? So now look at this one. This one predicts, in a way, that the average price of a new mobile home is going to be anywhere between $65,330 to $70,000 and $130. Now, of course, it missed that $65,000 by $330. But the point being is that the mean is not in that confidence interval. Now, if you look to the right, by the way, so this column says no, yes, 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 yes. So almost all of these contain the mean except one of them doesn't. Now, that's that's sample number 15. 1 out of 20 that does not contain the mean. Now, 1 out of 20, that means about 5%. That means 95% actually do contain it. And this is what this sketch to the right shows. So the first confidence interval goes from 63,000. I'm looking at the lines now, horizontal lines. The dotted line is where the mean is. So if you look at these, the first confidence interval actually captures the mean. This one captures the mean. So does this one, this one, this one, this one, this one, and so on. Sample number 15 actually misses it by a little bit, right? By about $300. So nevertheless, it missed it. Now remember, in practice, we actually don't know which of these confidence intervals contain the mean. Keep that in mind. He's taken a sample of size 36, and he has repeated the experiment 20 times. Usually, you don't repeat the experiment 20 times, right? Most of us, we just go get a simple random sample, come back and analyze it. So who knows? Maybe I'm sample number 15. My sample did not capture the mean, but then I'm under the belief that, well, 95.44, the odds are in my favor that I have captured it. But notice this one does not. Now the dots, of course, these are the point estimates. And if you look at all of the point estimates except this one is right on. This is $65,070. That's pretty darn close. So this one pretty much nails it. But every one of them, well, this one kind of close too. 2 out of 20 came very close to 65, but the rest of them are off, right? So this is, again, just the nature of point estimation. With point estimation, it's a hit or miss. You either get it or you don't get it, that estimate. So that's why between the two choices, point estimate or interval estimate, we usually prefer interval estimates. I much rather give my estimate in the form of a range of scores than a single value. So now with 95.44%, oh, actually, let me see if I want to tell you about this one. No, I don't yet. Okay, what I want to do now is I want to go to StatCrunch and show you this real quick. We're going to look at a simulation of this example that he has done. So I have a page in my MATLAB open. Okay, this is for my statistics class, and I'm just going to go to StatCrunch. So this is, I'm showing you how to go there in case you've forgotten it. So you go to StatCrunch, click on the StatCrunch, and I like to get there from this option, data sets from your textbooks. You can go to the website either way. I'm just going to go data sets from textbook. Spin, 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 and okay, here it is. Now what I want to do is I actually want to do a simulation of confidence intervals. Okay, so I'm going to go to Applet, and we're going to, let's see, we're going to take a look at confidence intervals, and we're going to do this for a mean, right? That's in chapter 8. Proportions or percentages are coming later. I believe that's chapter 12. Now, I'm going to take a look at a normal distribution here, right? You can actually have it from other distributions too, but I'm going to take a look at doing this from a normal distribution. Let's say the mean of this distribution, we'll keep it the way it is. Just the default. 50 and deviation is 10, and your initial confidence level 0.95 as a decimal, that means 95%. Initial sample size of 10. Just going to go with sample of size maybe 30, right? Now, if I'm sampling from a normal population, by the way, then the sample size does not matter, okay? So I can actually look at samples that are smaller, just like 10, but I'm going to make that 30, just a habit of mine. I like samples of size 30 because of central limit theorem. Okay, and my interval is going to be what we're doing here is a Z with population deviation sigma S, or sigma, not S. That's what I want. Now this other portion, if you're interested, every random number generator needs what we call a seed. Use dynamic seed, that's good enough. Dynamic seed, I believe, uses the clock that's on the computer, or you can actually use a fixed seed if you like. You can, I don't know, put your favorite number, put your birth dates, whatever. Just gonna go 987654321. There you go. You can do that if you like, or just use dynamic seed. It doesn't really matter. And let me do compute. Now let's see, how many are we creating? Okay. And what this is going to do is, let me hit compute and you'll see what's going to happen. There you go. So it happened kind of quickly. Didn't give me an option as far as like how many confidence intervals do I want. So the default constructs 100 confidence intervals. So there you go. These are 100 confidence intervals. Now remember, initially we're sampling from a normal population whose mean is 50, deviation is 10, right? Now mean is 50. See, we know that. That's the population mean, and we want to estimate it. So our first sample here, let's say this one. This is sample number 1. Estimates the mean to be 49.736. That's actually not bad. That's pretty close to 50. And the standard error, that would be the standard deviation. That's sigma over root n, by the way, folks. It's not the sigma 10. Remember, sigma 10, that's the population for individual scores. This one is central limit theorem. So our first sample here, there you go, has a mean of 49.736 with a deviation of 1.6. And there's your lower limit and upper limit. Now, notice 50 is inside of that interval. So this is a good confidence interval, isn't it? Because it contains the mean, the true mean of 50. And so on and so forth. You can see these red dots here. These are the ones that actually missed it. Right over here, right over here. They missed 50. A few of them are right on. This one is pretty close. Look at that one. This one is pretty close. Look at that, 50.307. So that gives you the idea of confidence intervals. Now, up here, it tells you that your confidence interval level is 95%. How many of those have mu in it? Exactly 95 out of 100. This is happening the way you see it because we're sampling from a normal population. And type Z, that's the kind of confidence interval we're doing. We talk about Z confidence interval in section 8.2. And our deviation is 10 here. So what proportion is contained, what percentage is contained? It tells me up here 95% exactly for the 95%. And now if you look at this one, remember, out of 100, 5 of them missed it. Here's one of them that missed it. This one estimates the mean to be 57 almost. So there is a sampling error of 7 units. True? And if you look at this confidence interval, this one looks at a sampling error of just a little bit. Let's see, 50. This is about 1 and change. But let me go up here. I guess, yeah, that's not bad. 49 off by 1 point. So anyways, looks like 1, 2, 3, 4, and 5. There you go. This one missed it too. The lower limit is 48, upper limit 55. And let me see, our mean is 50. That should be inside the interval, so I'm not looking at the right one. There you go. This is the one that I'm on that salmon, whatever that looks like red, light red or salmon color. So this one estimates the mean to be about 54, so it's off by 4 and change, sampling error. The lower limit is almost 51, upper limit 58. So we're saying anywhere from 51 to 58, which is wrong because the mean is 50. So anyway, now let me do 1,000 of these. How's that? Boom. There you go. We just did 1,000. You can't see it, but it's there. Now, let me do 10,000, another 1,000, and another, and another, and another. Notice the number here is changing. I'm going to get as close to 10,000 as I can. Good enough. Went 523 over, but that's good. The more the merrier. So, looking at 10,000 confidence intervals now. Of these 10,000, oh, I'm sorry, actually here, total is 11,100. I was looking at the wrong thing. Okay, right in here. Total of 11,100 confidence intervals were constructed by StatCrunch. Of these, 10,523 actually include the mean, contain it. Now, if you divide 10,523 by 11,100, you're going to get 0.948. That's almost 95% that contain it. So you see, it's not quite 95% because this is simulated data. So anyway, I want to just show you. So this is what the idea of confidence interval is. A 95% confidence interval means if you just do this over and over and over like I'm doing right now, in the long run, 95% of these intervals will contain the true mean. Okay, so let's see. I'm going to do this 100,000 times. How's that? It won't take long. Looking at this number, right? And each time I'm generating 1,000 samples. Wow, there you go. 96, 97, 8, 99, and this is 100,100. Of these 100,100 confidence intervals, 95,000, better than 95,000 have it. So that percentage is, notice how close to 95% that is. And that was the theoretical level. Okay, so hopefully you get a grasp of how confidence intervals work and what we mean by a confidence interval. So with that, let me go back to my note now. Okay, now when we talk about a 95.44 confidence interval, so this is what we're looking at here. This is the sampling distribution of X bar. Okay, right in here. This is the random variable is X bar. Now, if we go 2 deviation above, 2 deviation below, right? Remember, that interval contains 95.44% of all scores. So, now here's how this 2 deviation above, 2 deviation below relates to the Z. Okay, so if you look at our Z scores here, the center is 0. The 2 deviation above on the standard normal distribution, that would be a Z score of 2, and 2 deviation below means Z score of -2. So therefore, if Z is 2 and here -2, that interval contains 95.44%. So in a way, my confidence level is 95.44. If I go 1 deviation above, 1 deviation below, that interval contains 68%. Remember, empirical rule said about 68%. So that's equivalent to a 68% confidence interval. For 68% confidence interval, you go mu X bar plus minus sigma X bar. Okay, and I can actually write that one for you just to help you understand this a little better. So the interval mu X bar plus or minus 1, just 1 sigma X bar. Okay, this interval corresponds to almost 68% confidence level. So 1 deviation is 68% confidence level, 2 deviation 95.44. And if I go, just to finish this off, plus or minus 3 sigma X bar, that's going to be what? Remember empirical rule? 99.7 confidence level. And as far as confidence level again, you may want to say, well, why don't we have 100% confidence level? Wouldn't that be nice? So for sure, I know where the mean is. And we could, well, it would be meaningless. 100% confidence level runs from negative infinity to infinity. That's why we don't use that. Otherwise, it would be nice. So now let's take a look at an exercise here based on what we've learned so far. This is an excerpt from the book. Okay. So we're in section 8.1 and we are looking at exercise number 7. Okay. This is, I believe, on page 328 of your textbook. Let me write that. This is page 328 of your textbook. Now, in this exercise, it has to do with fuel tank capacity of new cars. They took a simple random sample of 35 new model, yielded the following data on fuel tank capacity in gallons. And you can see the data here. Now, the author actually gives us right in here. You see that? He gives us the total of all these scores. Our sample size is 35, right? That's what sample size is. And I have actually, there we go. That's the sample size 35 that I've used down here. So in part A, the question reads, find the point estimate, remember a single number, for the mean fuel tank capacity of all new automobile models. Okay. So for this one, well, X bar is our point estimate, true? That's what that is. X bar is our point estimate, which I have right up here. That's X bar. To find the sample mean, I'm going to use the formula we had from chapter 3 earlier in the course. That's when you add up all the scores divided by the total, right? So I did. Well, he gave me 664.9. We have that. So I divided it by a sample size 35, and I got 19 to be an estimate of the mu. And that's what this is. So a single guess, a point estimate of mean of random variable X. That's for average for individual automobiles. Okay, that's average for individual automobiles on average have a fuel tank capacity of 19 gallons. This is for all, and that's what makes this work, what we call inferential. That means you have this for all of these new cars. You see that? Not just for a sample that we just found. So what we're doing is we are inferring, that means we're generalizing from the sample, from small to the population, which is the whole, the population at large. And here our population is all new automobiles. We're not talking about people. Okay, for part B of this exercise, the question reads, in part B, the question reads, determine a 95.44 confidence interval for the mean fuel tank capacity of all new automobile models and assume the deviation is 3.5 gallons. Now, again, the reason he's doing 95.44, that means 2 deviation above, 2 deviation below, right? We're going to change that in section 8.2, everyone. We're going to change that to any confidence level you like. So for part B, I've done the work in part B. So this is what's going on in part B. The top distribution is the distribution of individual. These are in here, this is the distribution of individual automobiles. Could be millions of them. And there are millions of them. But the key is that this is, or the point being that this is for individual ones. Okay, and that's what this population represents. The distribution tells us. A random variable is X. It has a center that's unknown. We don't know what the average fuel tank capacity for all automobiles are, the new ones. So by central limit theorem, again, whatever that unknown is, that's going to be the same as, the mean of this, the center of the sampling distribution of X bar. So let me erase this one, and let me emphasize again that mu of X, this is unknown. That's what we want to estimate. Okay, that's unknown. Now, according to central limit theorem, we have the sampling distribution of x bar. That's what we're going to use. And with that sampling distribution of x bar, it's going to be normal, right? So I have this normal distribution. And the center of this distribution is going to be exactly the same as the parameter we want to estimate, which is mu, the unknown. Now, 2 deviation above, 2 deviation below. I need to find the standard deviation of this distribution, which by central limit theorem, remember that's sigma over root n. Sorry, let me get rid of that. Okay, sigma over root n here. So I divided 3.5, that came from here. Sigma over root n give me 0.6, so the deviation of this distribution is 0.6. Now, remember, for 95.44% confidence interval, we go 2 deviation above, 2 deviation below. So remember, each deviation is 0.6. And again, I want to emphasize that we're looking at the random variable x bar here, not x. We're taking advantage, in other words, of the fact that the distributions are both normal, but the one down here has a smaller dispersion than this one. See, that one is 3.5, this one is 0.6. So why don't we use this? They both have the same center, true? We're trying to estimate this one. This is the unknown. Well, if that's unknown, so is this one. And if they're equal, why don't I use this distribution? Which in practice means, why don't we use a group of measurements, find their mean, and that mean will represent the population mean, or an estimate of the population mean, rather than just an individual automobile. Okay, so that's the theory behind it. And I went 2 deviations above, that's 19, plus 2, each deviation is 0.6. That made it 1.2. So you get your upper and then you get your lower limit of your confidence interval that way. So to interpret now the confidence interval, we are 95%, almost 95.44 to be more exact, confident that mu, the mean fuel capacity of all automobiles, and again, notice how inferential this statement is when we say all of them. Okay. When we say all of them, that means every single automobile, new automobiles. For new models, of course, these are new models, not older models. Is somewhere between 17.82 gallons and 20.2 gallons. Now, in part C, let me go back up here. In part C, question reads, how would you decide whether fuel tank capacities for new automobile models are approximately normally distributed? Notice, by the way, here, he did not make an assumption of normality in this exercise. You see that? Because his sample size is 35, there is no need for it. If that was a small sample, he probably would have said assume distribution of fuel tank capacity of all new cars follows normal distribution, something like that. Okay, so in part C, how would you decide whether the distribution is approximately normal? Remember, we have a number of tools in our disposal. We can use the stem and leaf, we can use box plots, histograms, but we're going to use the fancy one. We're going to use a QQ plot. So we use a normal probability plot, or a StatCrunch calls it a QQ plot, and I did, and this is what it looks like. Now, let me show you how to get this QQ plot from StatCrunch, okay? Because I'm sure you all like to do that. So I'm going to go to, remember how I got to StatCrunch from the main menu in my MATLAB. You click on confidence intervals, and we're doing, or these are home data sets from the book, the chapter 8 homework. We're doing number 7. So click on number 7, and it loads the data for this exercise. These are the individual scores for the sample of size 35, and there they are. This is it, all of them. Now, to get a QQ plot, you're going to go to graph, and we're going to go down, 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 and there we go. Here's a QQ plot. So I'm going to click on the QQ plot. Now, the only variable for this exercise is capacity. You can left click on this one time, just once, don't double click. Left click once and just go down. You can play around with this and see what good thing comes out of it, what's going to happen. I'm just going to do bare minimum on it, and that's all we need here. Now, remember, we want normal quantiles on y-axis. Make sure you check this box. And then hit compute. And there you go. You get exactly what I showed you in my notebook. And there it is. So that's how I got the QQ plot. And judging from this QQ plot, remember, if the data follows a normal distribution, these dots will fall roughly on a straight line, right? Again, this is as good as it gets, everyone. You don't expect every one of these to be on that straight line, on the red line. So this is doing a pretty good job. So we can conclude that fuel tank capacity of all new cars follows a normal distribution. Looks like majority of them are here, which is right around, remember the average was 19, but there's a good cluster of them here. You have a few that are over 25, 26, 27, like that. Okay, so let me go back to my notebook, and I just want to show you how I got this graph. Now you see where it came from. And there's the conclusion for part C. Fuel capacity seems to follow approximately normal. Okay, now in part D, last part of this exercise, it reads, must fuel tank capacities for new automobile models be precisely and exactly normally distributed for the confidence interval that you obtained in part B to be approximately correct? Explain the answer. Okay, well, the answer to this is no. And the reason is because in order for central limit theorem to work, the requirement was that the sample size has to be at least 30. So in this exercise, because the sample size is indeed it is 35, it's right in here, and that exceeds 30, we're good. Remember, n must be at least 30, and we don't have to assume normality. And there you have it. I think we are good for this section. We covered a lot of grounds here, and I'm pretty happy. And it looks pretty good. So hopefully you follow all of this. I know it's a lot of conceptual stuff, folks, but in chapters 8, 9, we begin into some conceptual stuff. But then later on it gets better. So hopefully you're okay with what we did. And this will conclude, I want to make sure there's nothing else. So this will conclude our work in chapter 8 and section 1.